I'll see a notice. All right. It's a great pleasure to have Shesh, who is at Aerospike now. I think he just joined like a year ago or something like that. But
Mhm.
Aerospike's been a company that's been around for a while. Shesh, I know Shesh from his time at Wisconsin, and he's a veteran in the field of databases. So real pleasure to have him virtually present over here on the CMU campus. And with that, Shesh, would love to get you going.
Hey, thanks, Jignesh. Likewise, it's been a long time since, we everyone virtually met. So great to meet you and great to meet everybody else, Andy and others. I can't see everybody in the room, but yeah, hi guys. Yeah, no, I mean, I joined Aerospike about 2 years ago, and I started off as the, head of engineering, but then I sort of transitioned into this role of chief evangelist where I'm trying to make sure we're talking about Aerospike and our technology to the wider audience and definitely to academia, including academia, right? So that's sort of the goal. Uh, what I'll be presenting is, of course, the work of, uh, lots of great engineers over the last decade or more. And so, yeah, we'll look into that. Um, yeah, without further ado, I mean, that's the sort of fast, scalable, geo-replicated has all the buzzwords in there. So hopefully we'll do justice to most of them. We'll see, okay? And I'll start with 2 or 3 marketing-ish slides, and then we'll get into, hopefully, into enough meat and technology that there can be a good discussion around that. Okay, if I can get so how do I, okay. For some reason, the advance is not working. What do I do here? Maybe I get to use this guy here. Okay. There you go. Okay. Yeah. So, yeah, we are, I mean, used in a surprisingly large number of Fortune 500 companies for various use cases, right? So, on the top, you see a lot of AI use cases like recommendation engine, fraud prevention, just as a feature store, for ad targeting, identity graph, and you see a bunch of logos there. And then as an infra, we are used for caching, for mainframe augmentation, for global data distribution, transaction processing, and so on and so forth. And this sort of gives you a who's who of customers across multiple verticals. All this just to say that, this is a database that has a lot of miles under it. That's the whole point I want to make. So when I speak technically, it's not like, these are being validated across multiple customer scenarios. This is just to say that, hey, this is something that keeps us awake at night, right? So how do we kind of keep pushing the efficient frontier on all sides? And these are usually things that our customers worry about: latency, throughput, the cost of infra, the availability, the quality. And quality has multiple meanings, but I'll leave it at that. Obviously, data scale, the features that we support, and consistency, right? Consistency as in CAP theorem consistency. We'll talk about that. Okay, so nothing there. I mean, motherhood and apple pie. Just a sort of a glimpse into the kind of scenarios we get used in, typically very very low latency situations where you need less than 1 millisecond real-time reads and writes, high transaction volume, high data volume, and yeah, with very low downtime. So these are the kind of things, and usually turns out that because of our efficiency, when we go in, we replace one of our competitors, and there's usually a 70 to 80% reduction in service. Okay.
Can you
And
can you share what that was? Is it Oracle or is it like another key value, like a
no,
distributed
it's
key value?
a key value store. It's a key value store. I mean, it's a more modern database. I mean, and this is not just one case. I mean, multiple cases, and we can happy to delve into that more. But yeah, not Oracle.
Okay.
And this is the last marketing slide, and then we'll get into technical stuff. But this is just presence. Typically, where we sit close to the consumer or the user. We are a real-time operational database. That's how I'd like to think about us. which means that we are the ones where the events are streaming in, consumer actions are streaming in, blah, 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 blah. Usually, we obviously, we are a key value database. That's how we originated. Of late, we have graph and vector, and if time permits, we'll just take a quick look at vectors. And then we kind of data flows out from us into various analytical systems, right? So whatever the analytical system is. So we are a real-time operational store. That's the best way to sort of describe ourselves, or a real-time database. Okay, so without further ado, then let's get started on the architecture, right? So we are, shared nothing database cluster, although, we're thinking about how to sort of migrate into a shared disk architecture as one of our future sort of things. But as of now, this is our bread and butter, shared nothing database cluster. Nothing new here. I'm going to assume, Jignesh, you should stop me if you think I'm going too fast, or or
No, I think this is great. Yep, this is wonderful. Keep going.
Yeah. Okay. So this is how to think about Aerospike in functional layers, right? So the lowest layer is the storage layer, which is a single node concern. You kind of are worried about how do you store data at that layer, right? And then the secondary index could have been a global secondary index, but in our case, it's a local secondary index. So the storage layer and the secondary index layer are both per node concerns, or intra-node concerns, if you will. Then you get into inter-node concern, like a data distribution layer, which says, hey, how do I shard my data? How do I partition my data? And then above that is replication, which says, well, how do I not only shard, but also make sure there are enough replicas for availability? And then there's a transactional layer that gives you whatever, in our case, strict serializability. And then on top of that sits a bunch of query processing layers, right? So for us right now, we don't have a SQL query processing. We just have graph and vector, which you can call query processing layer. I'm kind of loosely calling it that. Of course, our client APIs, which are basically single table APIs, right? So you can get, put, scan.
And Shesh, your queries are coming directly through an API or SQL, or what's the surface?
Through an API, typically, because of the real-time sort of access. We'll talk a little bit more, but through an API, client API. So the application, I might as well.
Oh, oops, we lost you there.
Integrates with what's called a.
Shesh, we lost you for the last 5 seconds.
Okay, I'll repeat. So the application is compiled with a client library. So we have client libraries in multiple languages, about 8 languages, Python, C, C++, C#, Java, Rust, so on and so forth. So the application compiles with the client library. And the client library is actually what I call a reasonably heavy client. We call it a smart client. And it knows about the data placement and stuff like that. So it actually does a one-hop access to to where the data is. Okay, so that's how a lot of the performance, the client, and as you'll see in the context of transactions, the client actually plays a coordinator role for transactions too. So the client is a pretty important part of the whole system. Long story short. Okay.
Yep, sounds great.
Yeah.
And if I recall correctly, Aerospike's, or maybe you were talking about the storage layer, it's written from scratch. It's not you're using RocksDB.
No, it's not using RocksDB. No, this is completely. So so that's we are going to talk about that storage layer, right up. So we'll talk about storage layer next. And again, for most of you, you don't need this, but just to say that, hey, people typically, very early relational systems, what they did was they had a block storage, which is the underlying raw byte storage, if you will. Then there is some notion of a record-oriented storage or record storage, and there is some access method. The key is those days, early relational systems, when we all grew up, everything was in place updates. Okay, so both so you kind of had some kind of a one level of indirection in your sort of record-oriented storage or record storage, and that allowed you to move records within the page or within the block, if you will. And then you manage free space within that, and that allowed you, some flexibility, so you could move records without changing their RID or record IDs, and the access methods would point to record IDs, and so everything was in place update, bottom line, okay? And then, obviously, come the internet era around the same time. Actually, it turned out that this is a problem that I personally also worked on at AT&T, and we were parallel to LSM trees, and so we created this thing called how do you incrementally organize the data that's coming in? In our case, the problem was actually AT&T had a bunch of call records that were coming in very fast. Those days, I don't know how many of you remember, but you had all kinds of billing plans. You could do friends and family, time of the day, who you're calling. Based on that, your bill is computed at the end of the month. So the records were coming in so fast that we didn't have time to organize the record in a fashion that was suitable for billing. And so we kind of co-invented these LSM trees, if you will, if you go back and, but anyway, the crux of LSM trees very simply is to say, look, let's not spend time doing in-place updates for writes because the write volume is so high. So I'm just going to, keep stashing, keep appending stuff. I'll first append it in memory, and then when memory gets full, I'll write it out to disk. And then when I need, larger runs, when my data keeps accumulating, I'll merge a bunch of sorted runs into one bigger run, and so on and so forth. So this was great for write, okay? But now reads have to kind of go through multiple, look up multiple points, if you will. Again, I'm going to assume you know this, happy to talk more, but the key innovation that I want to talk about is what we did here, right? So which is, we kind of said, look, again, for us, because we were doing a key value store, we had the same write throughput problem, but we could not live with the read throughput of having to read multiple, if you will, multiple LSM trees or multiple points, if you will. And so we said, hang on, but if all you're doing is a bunch of updates or even a bunch of inserts, as long as you could keep this in memory, the primary index in memory. So the primary index is what lets you, find a key value, right? Find a key where the physical location of the record is. I can do these out of place updates for the records. I can keep writing records out of place, and then I can clean up, garbage collect, whatever, because I'm doing copy and write or equal it, I can garbage collect later. But my core index itself, I kind of update in place. So in place update for access methods, out of place updates for data, if you will. And I'll talk a bit about why it's reasonable for us to give the memory that the RB tree or the primary tree needs. But I'll just pause there and just make sure. I know there's a lot on the slide, but the real takeaway is for data, we're doing out of place updates.
You have to speak up.
I have a quick question. So firstly, over here, green means it's more full and blue means it's less full, or an empty means it's empty. Like, is that the color scheme going on over here?
I'm sorry, you're a bit faint. You may have to relay the question, Jignesh, or move the mic or
Yeah, he's moving up to the microphone.
Okay.
So my question was firstly the color scheme over here. Are you saying that blue here means it's partly empty, green means it's completely full, and white here means it's like completely empty? Like,
Yeah.
I'm not sure what the color scheme over here is trying to indicate.
You got it. The white is fully empty, the blue is less than half full, and green is either completely full or more than half full.
Then my next question to you is, for when you're trying to pick what files to compact, how are you picking those? And also, over here, what is the structure of the data on the disk? Are you just laying them all out sequentially?
Yeah, it's just blocks one after the other. It's a volume. You provision a disk volume, and then you use the volume.
Yeah, so each block over here is probably a file, correct? So
it's not a file. It's just a block. They're not files. We could use a file system, but then that's a separate thing. We could have used an entire file system, but each block is definitely not a file. It's just we're using raw storage, raw IO.
I see. And they are within the block. It's SS table, right?
No,
No,
it's a sequence of bytes. No SS table. We have to forget all history here. Yeah.
I see.
Yeah, they're maintaining like the SS table-like structure in the previous slide with a bunch of indices and data percolating down. Right, Sesh? That's what you mentioned in the previous slide.
No, sorry. Okay, maybe, I'm glad let's spend time. No, so these two slides, maybe I'm confusing you with these two slides. This is just to contrast. We are not doing this. We are not doing this. This is just history. LSM tree is what RocksDB would do, what all storage systems would do. But we are doing this where what I'm saying is there is just one index, right? We don't have multiple layers of indices because that's what gives us the read performance. There's just one index. That index sits in memory. The data itself is, so a record when it gets updated is updated out of place, which means its position changes on the
Wait,
disk.
what happens on a
Position
crash?
changes on the disk, you update, you go just update the RB tree, you change the RID, you swizzle whatever its location, but that's in memory. So you're doing an in-place update of a data structure in memory, and you're doing out-of-place updates for storage.
What happens on a crash?
We rebuild the primary index. Great question.
So you go through the entire disk and then have to rebuild the entire index.
Yeah.
I have a question as well. Let me know if you can hear me. So
Sorry, I'm not able to hear people who are far away. Yeah.
Yeah. Just come here, dude. Just come here.
I have another question. Just a clarifying question. So when you say in place updates for the in memory data structure, are you talking about just updates to the keys, and then like all the like record storage, you're sort of move it, like you're not doing that immediately? Is that what out of place updates mean here? Like I see there's a write queue as well. Are you sort of delaying these writes?
So, okay, yeah, let me try to go over this again. Thanks for the questions. Yeah, the out of place update. Okay, let me just say what out of place update is. Out of place update is basically just saying I will not update the record. Let's say the record is in some location on disk, and I change 1 byte in the record. What early relational systems would go is they would just go change that 1 byte in the same place where the record is sitting. Okay,
Yeah.
That's called an in place update.
Yeah.
Come LSM trees, we said, okay, now we'll just do copy and write. If something changes, we'll take the entire record and write it in a new place on the disk. So there's a new version, if you will, newer version of the record that comes up, okay? And that is what an out-of-place update is. So we do the same thing like LSM trees as far as the data is concerned. The difference between us and LSM trees is that we maintain a single primary index in memory, whereas LSM trees have, each LSM tree itself would have an index. So there are as many LSM trees that are active currently, that many indices, and you need to go look up those indices when you're doing a read.
Yeah. All right.
Okay, so that's the contrast.
Right. But then effectively what you've done is RocksDB is almost effectively RocksDB has this uniform compaction system. Is it not effectively the same as that uniform compaction approach? So so there's a tiered level compaction structure that RocksDB has, but there's also the uniform one in which it basically leaves all of the SS tables. Well, I know there are no SS tables here specifically, but like it leaves all of its SS tables. It's SSD optimized, and they leave it all structured in like they don't have any order per se in them, and there is no tree level compaction happening, but more so that they're all congested together and they're being compacted when needed. Is that a good summary?
I think the key is, can they look up in order one time? I mean, everything is order one. Can they look up? So let me not say order one. I mean, because these are some constant numbers. But can they just look up one index and get to the record that they want? I think
don't
that's
have to traverse the version chain. Maybe what we'll do is let him finish up.
Yeah,
with
sorry.
this, and then no, you're totally fine. And then come back and ask more questions. Sesh, this arbitrary has to fit in memory, or can it be bigger? Do you need enough memory to hold the arbitrary in memory?
Okay, so when it's in memory, we are blazingly fast. That's really our secret. That is where we have, beaten all the 80%, 70% you see, is when it is in memory, it goes very fast. Let me motivate why it's in memory, but I'll answer your question. No, it need not be in memory. The short answer, okay? Short answer is it can be on disk. But let's talk about, why it's so valuable when it is in memory and why it's a good idea for it to be in memory and why that memory is best spent on this. So that's the real argument, right? Well, the first argument is it even feasible, right, for a primary index to fit in memory, okay? And well, again, it's a question of what is the ratio of memory to disk in most cloud instances, right? So typically the ratio of, memory to disk is 1:13, at least, okay? So what that means is if you have an average of a 2 kilobyte record, our primary index needs 64 bytes of overhead. So every record occupies 64 bytes in the primary index, okay? So if you have an average of 2 kilobytes, then the primary index will fit in memory, okay? In most cloud instances with local storage. Notice that this is a shared nothing architecture. We are talking about with local disk. That's also the place where you get all that amazing performance that we talked about before. Okay. The next question obviously is, okay, there is enough memory, fine, but why use it for primary index? Well, what else will you use it for? Well, most people will say, why don't you use it for caching, record caching? Okay. And our argument is, wait a minute, actually, that's not a good use. If you, in our case, right? Because record caching first of all, does not help with end-to-end latency. Usually the network is the bottleneck for latency at our speeds, okay? Number one, it's not like, memory versus SSD speed is going to save you from the network latency, okay? Memory is nanoseconds, SSDs are microseconds. That could be several hundreds of microseconds or almost a millisecond in network latency. So it's not going to help you with latency. But whereas flip side, having the primary index in memory, it is the orchestrator. It's like a traffic cop, okay? All the client reads, everything goes through the primary index. And the key is we can get to any record in exactly at most 1 IO. So the predictable real-time latency, that's what we get out of this architecture, right? Basically, in 1 IO, because the primary index is memory, we know where the location of the record is. We go get that record back. So it's a predictably, you can get things back in 1 IO. The next thing is, of course, the primary index is what gets used heavily during defragmentation or garbage collection. And that's kind of the reason why you want to keep it in memory and you don't want to trash from the disk. And finally, well, especially in ad tech, which is about more than 1/3 of our business, it turns out that many record reads are actually it's not found, okay? So you're probably better off finding that quickly using the primary index, okay? So again, all I'm saying is this is a sort of lessons we have learned over a decade of working with customers, and bottom line, when primary index, keeping it in memory, turns out to be a very good idea, unless your records are very, very tiny, okay? In which case, obviously, the overhead take an extreme. If your record is 64 bytes, then your primary index size and the data size are the same, right? Because there's 64 bytes of overhead for 64 bytes of record. In those cases, obviously, it doesn't make sense to keep the index in memory. Then you would keep the index on the disk, and that's what we call an all-flash, and which probably is my next slide. Yeah, you will.
Hi. Sorry, can I jump in with a quick question on your previous slide?
Yeah.
So this is really fascinating. Would you be able to give like a rough sense of a number for like huge fraction of reads? Am I thinking like 20% or like over 50% in ad tech do not find the record? Like just a rough sense of scale.
80%. 80%.
80%. And also for your primary index, is it like the entire index is often being used, or is it there's a hot region, cold region? Do you have a sense of that?
No, typically everything is hot. People use us for. There will be some hot keys, okay? For sure. A few keys may be hot, but it's not. In our experience, things are strewn across pretty widely, and people use us. Like I said, it's an operational data store. So mostly yes. The answer is, if you want predictable latency, then you're better off keeping things in memory. You're absolutely right. If you knew, for example, there was a much smaller thing that could fit, anything extra. So I do want to point out, I'm not saying caching is bad. Obviously, we are also doing caching. Just to go back to this slide, there's a post-write queue, which is kind of a cache. Okay, it's a recently written cache, if you will. So as much memory as we can give it to RB3, then you can give it to the post-write queue, which is a recently written thing. And there is a reason we cache this. And I'll link it up. I might as well say it now. This is for asynchronous replication. So our replication is actually built into the same database process. And it's built in such a fashion that most of the time, it doesn't go to the disk. So when I want to asynchronously replicate these guys, these are all in the right queue. They're all here, and I can just copy them from memory. Okay, and so that's one use case. For reads, we don't see that much locality, but you can obviously have a read cache in addition. So
Yeah.
not saying we can't have a read cache. I mean, definitely you can also have the read cache in addition, right? So no problem. Yeah.
Yeah, that was enlightening. Thank you.
Yeah.
And Shesh, you presumably also have deletes, right? So in the system, and probably a fair amount.
Usually, yes. They they have what's called time to live. But net, yes, there will be deletes.
And you delete it on disk, or you do some garbage collection and clean it up lazily?
That's a great question. No, remember, everything is what shall we call it? Everything is lazy in the sense of copy and write. I mean, everything you don't put right. So everything. So when you delete, you put a marker, and then during garbage collection that goes away. Yeah.
Okay, great. Thank you.
What was the design decision for the use of red-black tree versus another data structure? Because most people use skip lists or even B plus tree for the in-memory part of the LSM.
That was probably just a choice. I mean, I don't know. I mean, I'm not. I was not there when this was decided, but I'm guessing it was just one of those balance trees. They picked a balance tree that they were comfortable with. Nothing more than.
Right, thanks.
At least I don't know of any deeper reason. Let me put it that way. Yeah. Okay, so the data can be purely in memory. This is what we just we call a hybrid memory architecture, where the index is in memory, the data is in flash, and there are various things. I'm not going to belabor this point because I do want to cover a few more interesting topics. And again, I'll just point out to a bunch of things, research ideas that that are definitely things that we need to think about, but we have not necessarily spent time on. And the last one is really our going towards shared disk architectures and so on and so forth. But it's not like we have thought much about it. But these are all areas that we are super interested in thinking about. Okay, I'm going to spend just a few minutes on data distribution. Actually, in the interest of time, I'm going to pass because I do want to talk a little bit about both replication and transaction, because that's kind of novel. So let's just focus on that. And I know we are kind of 30 minutes in. Okay, I will pick up whatever we need for data distribution on the fly. Okay. So yeah, we support both sync and async replication. Typically, within a cluster is is a set of nodes that communicate with each other, is a separate operational unit, and then across clusters, we may want to keep things consistent. We use asynchronous replication within a cluster. Things can be sync or async. Okay, and again, I'm not going to tell you about what is CAP theorem. We assume the trade-offs there. So I'll delve into how we do what's called strong consistency or synchronous replication. Okay. And again, I will motivate why we came up with something very different from Raft or Paxos or anything else for that matter, right? And they're motivated again by our analysis of what I'll call practical scenarios. So let me first talk about practical availability nuances, right? I classify failures into two forms, right? There are independent failures where some random nodes will fail, and then there are correlated failures where entire availability zone fails, entire rack fails, let's say. And again, by now you've seen that obviously we use very high performance expensive storage, aka local disk, maybe sometimes network disk, even then the best performance that you can get because you want this 1 millisecond response times. So typically people don't want to have 5 copies, 10 copies floating around. So in fact, most of our what shall we call it operations operate at what we call RF2 or RF3, which is replication factor of 2 or 3, which turns out to be the same as if you in Raft or Paxos language, 2f plus. Our RF is the same as f plus 1. So 2f plus 1 is 3 or 5. So those are the two operating points, the most common operating points, 3 being much more common than 5, 2f plus 1, if you know Raft and Paxos. Our partition availability, and this is a key difference, is available even if one replica is up, okay? As long as the DB majority is reachable. So we don't depend on a majority of replicas being up. And as opposed to, let's say, a RAF Paxos consensus, which requires majority to be available. And just some math will show if you assume, let's say, for example, 2f plus 1 equals 5, f plus 1 equals 3, then you need f plus 1 replicas to be available out of 2f plus 1, that's majority. That's about 5 choose 3, which is 10. So you can, any 10 possible subset of 3 can fail. In our case, we fail only if we assign 3 nodes as the main replicas, and then we co-opt any database node as a replica on the fly. So if those 3 nodes fail, then the partition becomes unavailable. So there is almost a 10x difference in the availability. For such scenarios where the assumption is there are only independent failures, and majority of the database nodes are going to be up, or there is an AZ failure, in which case, you have either 2 AZs or 3 AZs. If you have 3 AZs, 1 AZ failure doesn't affect anybody, either in Paxos or within us. If you have only 2 AZs, then actually we have this interesting notion of a tiebreaker node. And even if 1 AZ fails, this tiebreaker node causes the database to have a majority and all partitions become available. Whereas in, after Paxos, if you just have 2 AZs, then one of those AZs is going to have, some partitions are going to have 2 copies here, 1 copy here. So whichever has 2 copies and that has gone down, that's not available.
So does the question then become, how do you place those 3 servers that constitute the DB majority? How do you pick those?
Okay, good question. So essentially, let's step back, right? So let's just say, let me simplify this. Let's just say there are 5 nodes, okay? Or pick 11 nodes, okay? Let's say there are 11 nodes in the database. Although typically, again, just to be clear, our clusters are of size hundreds, several big tens or hundreds of nodes, right? So, which is why majority is very unlikely to be available. So it's not like in a 100 node cluster, you're not going to lose 51 nodes randomly. I mean, that's a pretty black swan event. You might lose an AZ randomly, but not 51 random nodes. But coming back to your question, the crux of our algorithm is as follows, right? So let's say we have a bunch of nodes, 11 nodes, 51 nodes, whatever you want, pick your number. And then we run what's called there are heartbeats that are exchanged across all these nodes. So at every point of time, we have a notion of what's a cluster, okay? And what's a maximal cluster? A maximal cluster is the set of nodes that can talk to each other. It's a clique in terms of communication, communicability with each other, right? If you add an edge, if I can communicate with you, it's it's a clique. It's a maximal clique. And that becomes a cluster. The question first question to ask is that cluster, does it have a majority? Okay. That is does it have, out of 51 nodes, does it have 26 nodes, for example? If it has 26 nodes, you are a majority. And if a partition has 1 replica in that, then you are available. By the way, just to be clear, I have not listed all the conditions under which we are available. There are 4 conditions under which we are available. I've listed the most important one to contrast with Raft and Paxos. For example, we're also available if all 3, again, so assume RF equals 3, all 3 replicas, RF equals 3 for us means 2F plus 1 equals 5 for Paxos or Raft. We only write to 3 nodes at a time. If RF equals 3, if one of them fails, we co-opt a new node and we start writing to that. This is a pretty complicated protocol, and honestly, yeah, and it's under review right now, right? So this is in my opinion, this is definitely some really, really deep work here. But I'll pause and see if I've been able to answer. I know I'm glossing over a lot of details, but Jignesh, please feel free to push me. Yeah.
Yeah, I think I got the high level idea, but maybe the devil is in the details, and maybe we might skip that for now. Or
yeah, I'm happy. Like I said, like I told you, I mean, I'm trying to present multiple things, and then if any of these sound more interesting than the other, I'm happy to do a deep dive into one topic.
Sounds
right?
great. Okay.
Yeah. So think of this as a breadth first search at this point. So we're just doing a teaser presentation, if you will.
Sounds great.
Yeah, again, this is not that big a deal. There are enough, enough things for Paxos also that kind of don't do log-based updates. With both Paxos and Raft as presented, they do what's called they have what's called replication logs, ordered replication logs, and we kind of, we just update the database directly. We don't need, ordered replication logs. And again, more Paxos Raft details here. But the point is, we can actually, everything is completely asynchronous. Even Raft for good reasons. I mean, they want to make everything explainable, so they kind of made it simpler to explain. But view stamp replication, which is the other, tries to make things a bit more asynchronous than Raft. By asynchronous, we just mean that we're not waiting for each other to catch up. So when there is a leader change, you don't wait for all the replicas to catch up, which is essentially what Raft needs to do. So the replicas need to make sure that they have the same set of logs that the leader has, and then only things can proceed, okay, within reason. So we don't need any of those. Obviously, I'm only giving you the, what shall I call it? I'm not giving you the actual technology or actual algorithm behind it, but I'm giving you only what we think are the benefits. Like I said, happy to do a follow-up where we actually get into the algorithm. Yeah. I'm moving sort of to async replication. So we talked about synchronous replication, which is essentially that's what gives us the linearizability. So the synchronous replication basically guarantees that if you update if you update a record, all replicas are in sync. Okay. So you will not have a situation where you write a record and then you come back and read it from somewhere else. You read an old copy. You cannot get stale reads and stuff like that, right? So that's what linearizability gives you. This is asynchronous replication where you are going to allow stale reads across clusters. So, but the goal is very different here. The goal is more disaster recovery. The goal is more, taking a backup, things of that sort. That's what this is designed for, where you're taking a cluster, copying it, not copying it, constantly sort of asynchronously replicating it, classical asynchronous replication. And the goal is just, you want to minimize the lag between the source cluster and the destination cluster, if you will, right? So the key is, again, this is designed within the same database process. And I don't know whether you remember, I told you that post write queue. So there is the process within one database node reads it from memory typically and writes it to the destination process directly. Remember, I told you our clients are aware of where the data is on the server nodes. So similarly, you can think of one of the clients being embedded as an XDR client. So the source node has the equivalent of a client for the destination. So this knows where given data should go. So it directly sends it to that point. Okay. This is a Sigma 2025 paper. So I won't delve much into this because this is available, should be available shortly for you guys to, download and read. Okay. Okay, let's do transactions, which is probably our latest, what we did. We released this about a few months ago. Okay. So just and transactions basically, before I begin transactions, just sort of talk about, you guys are all familiar with serializability, I assume. So, but very quickly, people have worried for long about transactions that consist of multiple records that operate on multiple records, but with only one copy. And the NoSQL guys, the RDBMS guys worried about this. The NoSQL guys, initially didn't even worry about strong consistency. They only worried about eventual consistency. Then they started worrying about strong consistency. And strong consistency or linearizability basically says, look, I have multiple copies of a record and a transaction is updating that record, then all copies are consistent, okay? Or the reads will, any read coming after a write will definitely read that value of the write, independent of all failures within that system, right? So, so that's what the distributed systems. So from terms of academic community, this is the database community, this is the distributed systems community, and these two kind of evolved independently for the longest time, okay? And then they kind of collided. There was a brick wall, right? But they collide now when we have to reason about transactions, what I call distributed transactions, although distributed transactions in relational databases has a fairly different connotation, but just for our purposes, multiple records and each record with multiple copies. This is what NoSQL, NewSQL have to deal with, okay? Again, the setting is very clear. Maybe very quickly, if you're not careful, this is just saying if you don't have linearizability, you can do stale reads. I will not bother you. I'm also not going to bother you with this, although this is a fairly involved example. I will just give you the takeaway here, right? The takeaway is that if you're not careful with distributed transactions, you can have serializability, you can have linearizability, yet you can have very unexpected results, okay? So just serializability, just linearizability is not enough. That's the takeaway here. Again, happy to dig deep into it, but essentially this can happen. Yeah, I'll.
Mhm.
So that's the key. So what you need, of course, this is a problem. I mean, all of us know this. When we are done serializability, we don't want to support anything lower than serializability. All I'm saying is in distributed databases, you don't want to support anything lower than strict serializability. By the way, just as a record set, serializability and strict serializability are the same when you have only one copy of the data. So that's why databases did not have to worry about strict serializability, because that was guaranteed. That was granted when there's only one copy of the data. It's only when you have multiple copies you get into all these trouble. So net anyway, all strict serializability says is, look, it is serializable, just like normal serializability, but you also have to obey, you also be real-time compliant, okay? Which means that if a transaction, this gray one, finish after the blue one, then that gray one comes after blue one in any equivalent serial schedule, okay? One of the things serializability allows is to time travel. You can take a transaction, if you just wanted serializability, you could take this transaction and put it anywhere in the serial order, even though in real-time order it comes later. But that's what is not allowed by strict serializability. And yeah, I'll just in passing say that. So the way we built, Aerospike 8 is the one that has this distributed transaction capability. The way we built it is on top of strong consistency or the linearizability that I just talked about. We are very well known for having very high performance reads and writes, and we didn't want distributed transactions to have any impact on that performance. So we had to design this in such a fashion that single record reads and single record writes were still, at the same performance. We wanted to guarantee strict serializability.
And so, Shesh, when you mean this guarantee, is it like similar to the way Spanner does, or
I mean,
I don't know if there's a quick answer to that. Like, could you compare or contrast that with the properties that Spanner provides? Means, do you have to deal with clock skews and stuff like that underneath the covers to make the guarantee that you're providing?
We don't deal with clock skews, but we give the same external guarantee. I'll come to that.
Okay.
Okay, but you're right. It's the same guarantee. Only Spanner and us. Actually, you know what? Why don't I just skip over to that slide, and then we'll come back and we can look at what is the state of the art in other databases, right? So Spanner provides strict serializability. It also provides what I call lockless read-only transactions using MVCC. Okay, which means that read-only transactions can operate on older snapshots because you have multiple versions. This is a classic timestamp multi-version concurrency control. It also uses something called, like Jignesh was saying, true time to guarantee globally synchronized timestamps. Okay, FaunaDB is the other one. They just, I think, stopped as a company, but they were the other one to provide strict serializability. This is Abadi's company. Abadi was involved with this company from Maryland, right? So again, they come at it slightly differently. Foundation DB is the other one that claims they can do strict serializability, but again, we're not seeing anything that scales. Cockroach and Gigabyte are the real NewSQL guys, but they can't guarantee strict serializability. Again, like Jignesh was saying, it comes down to because they also use global timestamps that to guarantee serializability, but they don't use this expensive hardware, atomic clocks and GPS and stuff like that Spanner does. So they have to, either wait. There's something called there's a drift, natural drift across nodes. Either you have to wait for that drift to pass before you commit a transaction, which can be several milliseconds, or you just don't wait, and they don't wait, and so they capture many situations, but they can't take up the causal reverse that I kind of glossed over, and therefore they're not serializable. So your natural question, I think Jignesh is asking, is, so what do we do? Well, the most important thing is we don't use timestamps for concurrency control because we don't do versioning, okay? So we don't do multi-versioning. So we just, the answer is actually pretty alarmingly simple, and I'll come to that. But so yeah, there's no dedicated hardware, there's no software vector clocks, so we don't do timestamps. We actually do a combination of OCC, optimistic concurrency control, and 2PL. I'll talk about it. Optimistic concurrency control for reads and 2PL for writes. Okay, and I'll also motivate why we made those choices, and we'll see. Real life, experience will teach us whether we need to tweak this further, or whether we'll learn as our customers start giving us feedback. But one of the reasons why some of the design goals we had, we made was we said, well, remember I told you our client is a smart client, a fat client, whatever. So it is actually the coordinator of transactions. So there is no extra level of indirection within the server. So we don't waste, one more level of indirection. Again, remember we want everything to go in millisecond time frame, right? So everything is very fast. The client actually maintains both the read sets and the write sets. The read sets is what we use for optimistic concurrency control. I'll tell you why we need the write set later. So you just use the read set as you read, maintain the version number at the version that you read. At the end of the transaction, you do a validation, read validation, and if the read validation succeeds, at least the read part of this has succeeded. Okay. Now, obviously, there is no locks for reads, and there is no need for replicating the locks, and so on and so forth. Okay. Now, for writes, actually, we use what's called a dual record notion. So, you remember I was telling you the record is stored on disk, and there is a primary index that points to the record. Well, guess what? We have a primary index that will have some information that says I'm pointing to 2 records, or it'll have an extra pointer to another record, if you will. And that is actually serves both as an atomicity primitive and a lock primitive. So it's a 2-in-1 thing. And how? Well, because we have the original version, the provisional version that acts as a write lock. So there is no other separate global lock manager, or we don't have to worry about replicating locks. The replicating locks happens just because the record itself is replicated, right? So what happens is that there's a dual record on disk. Because this is built on top of strong consistency, it gets replicated somewhere else. And if for whatever reason this node were to fail, the other node will recognize that there is a dual record here, and therefore somebody has locked it. Okay. So we don't use any write-ahead logging, because we have the before image and the after image. So we don't need redo logs and undo logs. And we'll talk about how we use this before image and after image. So we're not storing logs separately and data separately, right?
And when this write happens, it's happening on multiple nodes, right? Because if a single node fails, you don't want to lose that write.
Yep, exactly. Absolutely.
And then is there some guarantee about the readers in terms of what is their serialization order if they are working on the same data object as a writer, but the reader started after the writer? Do you have to worry about that case or no?
Let's step back a bit, right? So this is, okay. So if you know what's a precedence graph, right? So let's draw a edge between 2 transactions if there's a conflict between read-write conflict, write-read conflict, or a write-write conflict, okay? So what OCC and 2PL together ensure the way we do it is that there is no cycle in the precedence graph, okay? And we'll just worry about serializability for now. And how do they guarantee that? Well, as far as reads are concerned, it's very simple, right? So all we are doing is we are saying, look, I'm going to continue reading without obtaining any logs. By the way, sorry, what I did not necessarily say is if something is, if something is being updated right now, then the read will choose not to. I mean, it could have gone ahead and read and stored the version. In our case, we choose not to go ahead and read the version. We assume that the write will succeed, so we kind of fail right away. But even if we went ahead and read the version, it's fine because we have a check at the end, which is saying, has anything that I've read changed? Okay. If it
I
does
see.
not
So you
change,
validate the read set at the end. Yeah. Hackathon does that too. Okay, I see. So the commit order corresponds to the serialization order then. Is that what you're saying?
pretty much, yes. We stick to PL, so the write locks are held until the end of the transaction. The commit order is technically the same as the commit bit going. Well, I'll talk about the commit bit going to disk, but yes, that's pretty much the commit order.
Okay.
Okay. Okay. So just one more detail. The client ensures transaction atomicity in the sense that it knows the write set. Remember, I told you it also knows the write set. So on abort, it rolls back each item to original state. So it goes and tells every record, okay, so you can get rid of your dual, go back to the original. If you commit, then it says rolls forward asynchronously. Okay, so it's not part of the transaction. It rolls forward asynchronously, lazily, if you will. Now the monitor is another construct we introduce just as a backup coordinator. Remember, everything else has replicas and replicated. The client is not replicated. It's part of the application. So as long as the client is alive, it can do its job. But if for whatever reason the client dies, there are two possibilities, right? So the client never wrote anything. Actually, if the client never wrote anything, then there is no monitor record at all created. So you need to create a monitor record only when the client actually writes something, okay? When the client writes something, it immediately tells the monitor record, I'm going to write this, okay? And so there is a bunch of, before writing, it registers what all it is writing before writing. And then it's the commit bit in the monitor record is the atomic commit action, if you will. There is no more, we don't need to do any distributed commit because this, of course, underneath that record is replicated. This monitor record is replicated just like any other record and so on and so forth. The whole point of this is this monitor record, every transaction has a timeout parameter that it starts with. If the monitor record recognizes that a transaction is timed out, then it will either roll forward or roll back based on the state of the commit bit. So it looks at the commit bit.
Seshan, we have the other guys coming in the room, so we need to wrap up in like 3 minutes. Sorry, I know we've been bothering you with a lot of questions.
No, that's fine. I mean, we should actually, I would rather stop now. I mean, just want to say that, look, there are, I mean, then the next big thing we're doing is vector search. And I mean, obviously, we can't do justice to, there are many topics we could talk about, but I'm going to stop actually.
You could take a, you could take a couple.
No, this is fine. Let's take a few questions if there are any. I know I went very fast, but there could be questions.
No, we were bothering you with a lot of questions. So this was great. First, let's thank you.
This is a dual record. There's just two.
Do you want to come up?
Yeah, question was I don't know how a dual record works. So is it you're storing two versions of the data and like I assume
the old copy and the new copy.
The old copy, new copy, and like so what with the write conflict you just fail. Okay, never mind. That's how you're locked. So you're just checking if the new
there's no lock because the pointer in the tree ends up becoming the point of control, the way I understood what Sesh mentioned.
Yeah, the fact that there are two versions, there is a latch obviously every time you update something. I mean, but the lock, as in long duration lock, transaction duration lock, is the two pointers. Yes.
Yeah, that makes sense. All right, great, thank you.
And then presuming your transactions are they don't tend to write to lots of objects, right? They tend to be small in terms of the number of objects they write to. And that's kind of what you have optimized for.
Exactly.
Okay, got it.
Absolutely. It's optimized for what I will say low conflict.
Yeah.
Even
yeah.
I mean, if there are tons of conflicts, then this is unlikely to be the best design. Okay. But our thesis is that this is the right design for the kind of workloads we are seeing, but honestly, we'll need to validate this.
Got it. So in
So
ad tech, it's like you're writing new records for new bids, and then you are searching for records that correspond to the same campaign and bids for that, right? So you have lots of new records, but not lots of reads, but you don't tend to have lots of writes simultaneously in the same transaction. Am I getting that about right in terms of what your workload looks like?
No, I mean, for ad tech, yes, I think the initial workload to be more general is we force people to not denormalize many times because that's what we say. But now we say you can normalize a bit, okay? We will normalize as much as you want. So you can update related records together fairly in a transaction very easily or very quickly. Now, we will continue to evolve and see how this works for very more general purpose transactions, but you never know. I mean, this is a starting point for journey. Yeah.
Great. Wonderful. All right. We've got a little crowd outside the room. So Sesh, thank you.
Thank you. Bye, guys.